If you have not passed the mastery yet, so if in the mastery column you still have 0, you have to get into someone's office hours and pass that. You have to keep taking it till you pass it. That's the rule. Okay, so get in there. You have the rest of this week and all next week. Anybody's office hours. Okay, exam 3. Exam 3 is a week from tonight. So if you go to exam solutions, homework solutions, and exam prep. Homework solutions and exam prep. I put the folder there for exam 3. Maybe? Where is it? Oh, it's still working? Internet's not coming in yet. Oh, here we go. There it is. So exam 3 and related quizzes. Now, the review sheet and the quizzes are all based on a previous semester, but the topics are the same, okay? And the quizzes are close. All right? So the review outline has these dates that were actually from a year ago. So just ignore the dates. Ignore the dates. But all the topics and the headings of the topics and the individual topics are all accurate for us, okay? And then the quizzes, these are all solutions and blank versions from last year's quizzes. So they maybe you're going to see a lot of similarity, a lot of overlapping problems, but then some things may be a little different. And then we did not have quizzes on these two quizzes, 9 and 10, which are related rates. This one particularly. Related rates is what we're going to do today. And inferring from rate, we never had a written quiz on this, so this will be something new to you in terms of a quiz, but it's all great practice for the exam. Okay, so all these quizzes, blank versions and solutions, are the same material we covered, and we'll have a lot of overlap with the actual quizzes we did, but then there may be other stuff there too that's all important. So it's all good study problems for the exam. And that's, again, a week from tonight, same procedure as usual. Any questions on exam 3? So exam 3 will cover through related rates. That's what we're going to do in class today, and your homework for Tuesday. Then Tuesdays and Thursdays material is kind of the culmination of the course. We're going to get into the fundamental theorem of calculus, and that's all very important on the final, but not on exam 3. So it's like 25 to 30% of the final exam is next week's stuff on the fundamental theorem. Okay, but it won't be on exam 3. Questions? And so with exam 3 and the final exam, we're like, that's over a third of your grade. Like maybe close to 40% of your grade is still yet to be determined on these exams. So, time to hit the books in calculus, okay? Because things are not set. You have still a lot of room to improve. And then also, in terms of the final exam, if you do better on the final exam than your overall calculated score in the course, according to the syllabus, then I'll make the final exam worth more. So like I'll average in the final exam one more time, and then the final's worth something like 50 or even more % of your grade. Because you only went for those students who do better on the final than what you did all semester. Okay, so there's still a chance to get that higher grade that you were hoping at the beginning that maybe you didn't think you could get. But it's going to take the right performance on the final. No, just a higher proportion of your grade will be the final. Yeah. So for individual students, if you do better on the final exam than your overall performance for the whole semester, I'll just weight the final more. But if you don't do better in the final, you'll get what I promised on the syllabus. Okay? Yes? It is multiple choice. Yep. Yeah. Oh, so yeah, and I will drop I'll drop like 2 lowest quizzes and 2 lowest written homework. I'll drop those. But I'm not going to drop any exams. So drop the 2 lowest quizzes. Hold on a second. I'll drop the 2 lowest quizzes, 2 lowest homework, and for web work, I will make an adjustment to that I know there's technology issues and things that happen. So I will make a significant adjustment to your overall web work before I mix that into your homework score. Yeah.
Is the exam next week multiple choice too?
Yep. It's just like the others. Yeah. Yeah. At the very end. Yeah, so when I calculate your like after finals, when I'm calculating your grade, then I'll put the top in and also. And also given a technology adjustment for that too. So those web work and top hat, I'll make an adjustment because I know it happens. There's things with technology that hurt you a little bit, so I'll give that back to you. Other questions about that? Okay, so please remember all of that when it comes to evaluating me online. Maybe we'll, at the end of class we'll do that today. All right, so what are we talking about? Let's do one example from the web work. What happened? That's the wrong one. That's today's. I mean, number 4. Okay, so what happened with 6? I bet lots of you got this right. But this is like the kind of the technology thing I was talking about. If you put an exact answer in as a fraction, you got it right. But if you put any decimal approximation in, even 8 decimal places, correct? You didn't get it right. So a couple things. Whenever you can put in an exact answer, put it in an exact answer, like a fraction or an expression. You can let web work be your calculator. Okay? You can put in an expression with parentheses, and that's what's nice about preview answer. So I could come in here and I could say, 3 minus pi divided by, square root of e to the 6th plus 8, and then times 75, okay? And then I can go to preview and I can get a nice visual image of what I put in there instead of trying to figure out if all my parentheses are correct. Okay, and that doesn't waste an attempt. It gives it, and it tells you then it will be the calculator for you. So that's like an exact answer, and the preview will show you a nice image to make sure that it's what you intended to put in with all the right parentheses. So put in answers like this, wherever you can. Then you don't have to worry about decimal places. You can use preview to make sure that what you're putting in is correct. So that's what happened on this one. That's what happened on this one. So if you didn't get it right, again, so I'll make the technology adjustment when I compile the web work scores. The one I do want to do, though, is number, I want to do this one, just to do one example. This is the one that had, and this is a good example of when we put it in, we can use the preview without wasting a attempt. Make sure it looks like what we want it to look like. Okay, here we go. I'll do it fast. So we're going to do basically doing the rate of change with respect to x of each side. So if those expressions are equal, then their rates of change with respect to x are equal. And so rate of change of square root is 1 over 2 square root times the rate of change on the inside by the chain rule, which would be 1 plus y prime. How many terms did I just get out of that? How many terms are on the left side now? There will be 2 terms, right? Because it's that thing times a sum. That will give me that's going to give me 2 terms on the left. Okay? This is going to be 0 plus product rule 2xy squared plus x squared times 2y y prime. Questions on the first step? Taking the derivative using the square root rule and then using the product rule. Okay, so now this, like I said, this is going to give 2 terms. That thing times 1 and that thing times y prime. The one with the y prime is going to stay over here on the left, and I'm going to move this one on the right and subtract it to move it over. When I do that, I'm going to have y prime times 1 over 2 radical, and then minus this, x squared 2y y prime. And then this first term, that when I multiply, I'm going to subtract that over to this side. So negative 1 over 2x plus y. And then plus 2xy squared. So on the left, I got two terms. I got 1 over 2 radical x plus y times 1, which I subtracted. And then I got that same fraction times y prime, which I just left here on the left. And then this one with the y prime, I subtracted and moved over. So I factor out, and then I'm gonna what? Then I'm gonna move this to the denominator of that right side, and that's my y. That's gonna be my dy dx. So I'm gonna put this in my numerator. That'll be my numerator, and then that thing in parentheses times y prime will be the denominator. Let's put that in and use the preview. So here we go. It'll be. So yeah. So this is where we really need the preview because this is going to be a kind of a nasty expression. So I'm going to have negative 1 divided by 2 square root of x plus y plus 2xy squared. There's my numerator divided by 1 divided by 2 square root of x plus y minus x squared 2y times 2y. So when you look at that in the entry box, it's like, how can I know if I've got that right or not? It's so hard to see. That's the beauty of preview. So, is that what I wanted? Negative 1/2. Oh, see, look, it's not right. See what happened? Those radical x plus y's didn't end up in the denominator how I needed them. So I just saved an attempt because this is not what I wanted. Okay? So what do I need? I need 1 over, then parentheses around that, 2 square root x plus y, and then parentheses around that, 2 times square root x plus y. Now preview again before we use an attempt. How's it look? Is that what we wanted? Negative 1 over 2 squared root, yep, plus 2x squared, right? 1 over 2. I think it's right now. Or it's exactly, it's what we got anyway when we did the algebra. We have it entered correctly, so then now we're ready to see if it's right. Question? Yes, please.
Okay, how did you get the negative 1 over the 2 square roots of x, y?
Okay, so I multiply. So this, do you see how I had to distribute this? Yeah. And that made 2 terms. So this first term is going to move to the right side of the equation because it doesn't have a y prime. The second term with the y prime is going to stay over here.
And you can't just add those 2 terms together because they have the same denominator?
No, because the one that has the y prime has to get over here to the left, and the one that doesn't have a y prime has to be to the right because we got to isolate y prime.
Yeah.
Does that answer it?
Well, like say you didn't want to do that, would you add them together?
Yes.
Yeah, if that didn't have a y prime, then you could treat it all as one thing and move it to the right. But if one of them's got a y prime and the other doesn't, we got to get those apart because we need the y prime terms over there and the non-y prime terms on this side. But if it was 1 plus y, then now that whole thing can be considered a single term to be over here. Yeah. Other questions? Don't be so hard on yourself. Okay, so let's move on. Here we go. Then the homework. There's the homework for Tuesday. There's 15 questions. To get full credit, you can do any 10. Any 10, and if you want to do more, you get extra credit. Okay? So any 10 will be full credit on Tuesday's homework. Okay? Yeah. All right. Okay, ready to start? Here we go. I got my list today. Okay, here we go. All right, so there's a ladder. vertically against the wall, and then a tricky monkey comes along, and he kicks the bottom of the ladder out so that the whole ladder slides down the wall like this. That tricky monkey. Okay. So the question is, how fast? And like we talked about with these application, real world situations, we want to understand the situation before we just try to dig into doing things to get an answer. All right. So how fast is y, the distance from the top of the ladder to the floor, changing with respect to x, the distance from the bottom of the ladder to the wall? So first question is this an optimization problem? Is this an optimization problem? That's the ones you've been doing. Because why not? So it's not asking us about maximizing or minimizing a particular quantity. It's not saying what's the most something or what's the least value of something. It's asking us, what is it asking us for? It's saying, how fast is y changing with respect to x? What is that asking for? Rate of change, right? It's asking for the rate of change of y with respect to x. And this will be a function, right? So that's going to change for different values of x. The rate of change of y with respect to x is going to be different. Okay? So let's pause it here. Oh, that doesn't pause it. Beautiful. Okay, right there. So we'll pause it right there. And so our quantities, they're telling us the quantities. Y is the distance from the floor up to the top of the ladder. X is the distance from the wall to the bottom of the ladder. The ladder is 10 feet long. Okay? The ladder is 10 feet long. Okay? So how can we represent the quantity being asked for? dy dx or y prime, right? We know that. So the quantity being asked for is the rate of change of y with respect to x. So we could use dy dx or y prime. So we want to determine y prime, and that's what you were doing in your homework. So what do we need to do that? What do we have to have in order to determine y prime or dy dx? Okay, so it's not necessarily a function anymore. Okay, but yeah, you got the right idea. So in your web work problems, you didn't have functions, but you had what? You had equations of x and y. So where did we get dy dx? We started with, and what was always given to you was an equation of x and y. So that's what we need to come up with here in this problem. We're not just given us. We need to come up with a relationship between x and y that holds true. So then we can use our implicit differentiation to get y prime, or dy dx. So now it's up to us to come up with that initial equation that in the web work you were just given every time, right? You were just given some equation of y and x every time. So let's see if it was on top of this here. So where's Trista Thacker? It's Trista. Can you see how we might make a relationship between x and y in this scenario? Like what equation will bring together x and y? What's that?
I'm not sure.
You're not sure, okay. So what does that form? Do you see what that forms right there?
Oh, I'm trying.
Yeah,
So,
yeah, and what would it be?
so it would be 5.
But x and y are changing, right? X and y are changing, so we don't want to assign a value for x or y.
So x squared plus y squared equals 10 squared.
That's it. Yep, that's it. So, and does that always hold true as x and y change? Does that always hold true?
Yep.
How about now? Is it true now? Yep. The ladder is a fixed quantity, right? It's a constant quantity. It always is 10. And then we always get some right triangle with x and y as the legs. So this is always true as x and y change together, right? So x and y are changing together, but that holds true no matter what the configuration is. So here's a different configuration than the one we saw before. Okay, so find dy dx. Go, find dy dx. You've done this now, right? Okay, where's Marin? Marin Jackson. Is Marin here? No Marin? Okay, how about Vinay Chan? Vinay Chan, not here? All right, how about Ty, white hair? Tay, where's Tay? I think he might have dropped. All right, where is Ella Alcantar? Last name, Ella Alcantar. Uh-oh. Rashid. Alman. Rashid. Dong Yu. Ho. Oh. Andrew. Islis. Where's Andrew? There we go. How did we do in this? Tell me what you did.
We x plus 2y, y prime equals 0.
Okay, and so then you solve for y prime, and did you get something?
It should be negative x over 2y.
Which simplifies to negative x over y. So you should have gotten the dy dx was negative x over y. Negative x over y. Okay, so what does this tell us? This gives us for any configuration of x and y, it'll tell us how the top of the ladder is falling per change in the bottom of the ladder. So what will the units be for this rate of change function? What will the units be? Where's Hassan? Kurt? Hassan? Yeah. What will the units be on this rate of change function? Did you say something? What did you say? Not sure? Okay, where is Jared, Sue? Yeah, Jared. Units of the rate of change function. Feet. Feet per second. Agree? Feet per second. Is it feet per second? So this is the change in y for a change in x, not change in time. It's not feet per second, but it's a change in y per change in x. So what would that be? Feet per feet. Feet per feet, okay? So it's how much vertical feet changes per change in horizontal feet. So you don't want to cancel them out and say it's a unitless thing, right? They're two. You got horizontal change in feet, change in distance versus vertical versus horizontal, right? So you want to leave it as feet per feet. Yeah.
Can we just like what work we need to simplify answers?
You don't. You can let what work be the calculator. As long as you have an expression that's equal to a simplified version, it should give you the right answer.
And then will the exams be in simplified answers?
If appropriate. So like on the master exam, it was just about knowing the rules. So we didn't, it's kind of case by case, whatever's appropriate in the situation. Yeah. But normally you do simplify, and you especially simplify like really obvious things. So normally, okay, I'm still answering your question. So yeah, normally you simplify especially very obvious things. Like this, right? So this is very obvious that you want to simplify that. Okay? But you don't want to spend 5 minutes rearranging something just to get it a little bit simpler than it was before. So it's kind of like case by case basis. Yeah, please.
So I know earlier when we were looking at the function originally, you said so you said we can write the rate of change treating it as points, right? We couldn't the very first thing we looked at here, we did an equation that wasn't a function, right?
Right.
And we said that we couldn't find the rate of change of the function, but we could treat it as points and find the rate of change of each point.
Right, like we think of the independent variable as an ordered pair.
Yeah.
And this is the same thing here.
Okay.
Yeah.
How do we distinguish that we're doing that and not doing it with the function? Is there a
what is your original equation? If your original equation is y equals an expression of x's, then you have a function, and you can write the rate of change as a function of x. But when y and x are like intertwined and we can't really separate it out so that you get y as a function of x, that's when we use implicit differentiation, and often our rates of change will be in terms of both quantities, x and y.
But there's not like a difference in the notation. It's still dy over dx.
Right, because it's still finding in that localized area. In that localized area, it's still finding the same rate of change we've always found, but you just need both coordinates to get the value. Yep. Okay. So how fast is the top of the ladder falling when it's 8 feet above the ground? When it's 3.5 feet above the ground? Go. So is Gunnar here? Gunnar? No? William Clark? Where's William? Do you see a kind of a roadmap to answering this question?
So y is 8.
Mm-hmm.
The change in y would be 2. So you take that from dx.
So how are you seeing that the change in y would be 2?
If it's starting at 10, right?
Okay, so this is asking about the rate of change right at the moment when it's 8, not for the whole 2 feet. So we want the rate of change at the moment when y is 8, not over that change. Does that make sense?
I got it.
Okay. So we're after this. What do we need to find dy dx? Yeah, so we need x and y, right? We need x and y, and our y is 8. So can we get x? How are we going to get that? Yeah, and that's kind of the situation I'm showing here. That we can just assume that's 8 right there, just close enough. So we can use this then to get the corresponding value for x. If y equals 8, anyone got it? 6. So if x now we've got everything we need to get that rate of change, which is negative 0.75, 3/4. Yeah.
Other than being logical about it, is there a reason why we don't say 6 and negative 6?
6 and negative 6. Yes. Looking at the situation. So what's the domain for x in this situation? It's only positive values. So yeah. So now we're looking. You're right. Solving that for x would give 6 and negative 6. Absolutely. And then we look at the situation and say, what is? There's no negative x values here. We're only talking about positive x values. So we throw out the negative 6. Good point. Good point. Okay, for 3.5, anyone got the x value? Square root of 80.75. Agree with that? Is that right? 87.75? All right, and when we put that in to negative x over y, we get negative 2.67. Okay, so I want you to interpret these values individually in the context. What do these numbers mean in the context? And then reason about them, looking at them together. So reason about the fact that this one is negative 0.75 and this one is negative 2.67. So individually, what does each number mean? And what do they mean in comparison? Why do they make sense comparing the two of them in the situation? Okay, go. Feet per feet. Feet per feet. Okay, where's Baotong Yan? Where's Baotong Yan? Okay. Can you interpret that number, negative 0.75? You know what the number negative 0.75 means in the context of the ladder problem? Not sure? Not sure. Okay. How about Eric Beshikan? Eric B. Eric B. How about Madison Halverson? Madison? Tay Whitehair again. Alejandro Ruiz. Alejandro. Okay. Whitney Eba. Where's Whitney? How about Mackenzie M? Mackenzie M. Pierre. Is Pierre here? Rachel Erickson. Rachel. Okay, we found someone. How about the number negative 0.75? Feet per feet. Okay. Yeah, she said. So when the top of the ladder is 8 feet up, what for a small change in x, the change in y will be negative 3/4 of that change in x. Okay. So when the ladder is 8 feet up and the bottom of the ladder is 6 feet out, for a change in x, the change in y will move down 3/4 of the amount of the change in x. And then similarly, when it's in this config, when y is 3.5 feet above, what happens? For a change in x, the ladder moves down, what? Almost 3 times as much as however much you change x. So looking at those numbers together and looking at how the ladder is falling, why does that make sense? Why does that make these numbers together make sense with how the ladder is falling? Yeah, Philip.
Because as it's falling, it's gaining momentum.
Right?
And it's going to slowly, it's going to fall down.
So up here at 8, so here's when it's at 8. If I change x by a little bit, how much did y change? A little bit, like less than the amount of x, right? Less than the amount of x. But down here, When y is 3.5, like this, I change x a little bit. Watch y. So I just changed x a little bit, and y changes a whole lot more, like about 2.5 times as much as the amount that I change x. And that's right, because as the ladder falls, we're seeing larger and larger changes in y for the same change in x. Okay, so questions on that? So that's kind of a real-world situation for all these problems that you were doing in terms of the implicit differentiation for homework tonight. So here's that. Here's what we just did. And we said that the expression gives the rate of change of y with respect to x, which is feet per feet. So as many of you, or one person said, and other people were thinking, what about how fast the top of the ladder is falling in feet per second? Feet per second. Right? So how fast is it falling every second? So we bring time quantity into that. So everything we were doing before, we weren't considering time. We were just considering the quantities x and y, and how fast y was changing with respect to x. If you want speed, now you got to bring time into the mix. So time comes into the mix. Okay? So that we'll have the time in seconds since the monkey kicked the ladder. The time in seconds since the monkey kicked the ladder, we'll call that t. Okay? And then we're going to say that the bottom of the ladder is sliding out at a constant speed. So we're going to have to assume that to make this kind of simple. The bottom of the ladder, we'll just assume that it moves across the floor at a constant speed, and that's actually what you were seeing there in that animation. Okay? So if that's true, then what? Distance equals rate times time, right? Distance equals rate times time. We'll relate that to calculus in a moment here, but just we know that. And so then that x distance is the constant rate that is moving out times this value t in seconds since the monkey kicked the ladder. Okay? So then dx dt, so if we want now these quantities in feet per second, then our derivatives are going to be with respect to time. We're going to take dx dt. And so dx dt will just be v. And so this dx dt then is the constant rate of change of the bottom of the ladder moving to the right or along the floor. So that this is going to be in this problem right now, this is a constant. But now it's distance with respect to time instead of distance with respect to another distance. So we start with the same relationship of x and y, but now if we want the rate of change of the top of the ladder with respect to time, what would that be symbolically? So how fast we are interested in how fast the top of the ladder is moving as a speed per second, then what symbolically represents that? How fast the top of the ladder is moving per second. Where's Desiree? Desiree? Okay, Christopher Heston. Okay, if you all conspire, Christopher's here. All right, if you all conspire not to answer, that's not going to change how I determine attendance grades. Okay, all right. So please answer. But here's Christopher. So, what notation or symbols would we use to represent how fast the top of the ladder is falling per second? What would that be? So I'll give you a hint. It's a derivative, right? It's going to be a rate of change, a derivative. So what derivative would it be? The top of the ladder with respect to time. Not sure? Okay. All right. Okay. All right. So how about where's Philip? So this, how fast is the top of the ladder falling in feet per second? How can we represent that symbolically with all the symbols and quantities that we have defined here? dy dt, right? dy dt. So if we want dy dt from this, we're not going to we're not going to do implicit differentiation with respect to x anymore. We're going to do it with respect to what? No, not y. T. With respect to t. So we're going to differentiate the left side now, not with respect to x, but with respect to t, and the right side with respect to t now. So that we get things like dx dt and dy dt. Okay? Instead of with respect to x. And so what do we get? We get so now everything's the chain rule, right? Everything, x is a function of t and y is a function of t, then everything we do is chain rule. So 2x, then by the chain rule dx dt, and then 2y, and by the chain rule dy dt. So not just the y terms are chain rule terms, they're all chain rule terms because we're differentiating with respect to time. And x and y are both functions of time. Do the math, and we're going to solve for dy dt. That's what we wanted. And we're going to get negative x over y dx dt. All right, so this was our constant rate of change, right? We said this is the constant rate that the bottom of the ladder moves out from the wall. And then we have this expression, and then that whole thing will give us how fast the top of the ladder moves per second now, because it's dy dt. So this is what's called a related rates equation, right? It's an equation that relates more than one rate. Huge point here. Simple but huge point. It's an equation that now brings together more than one rate in the same equation. It's the first time we've seen that all semester. It's telling you how the speed of the bottom of the ladder and the speed of the top of the ladder are related at any given time, or for any given x and y. And where did the related rates equation come from? What was the source of that? What did we have originally that we could get the related rates equation? The equation of the quantities for those rates that we're relating, right? So the equation of the associated quantities is the source for the related rates equation. This is a key part, because now we're building kind of your thinking as you're doing related rates problems. We need to get an equation that relates the important quantities from which we get the related rates equation. Okay, here's to reiterate. To get the related rates equation, you first must have the equation that relates the associated quantities. You first must have the equation that relates the associated quantities for those rates. So this is kind of like the big takeaway for approaching related rates equations. Like the big takeaway for approaching optimization problems was what? A function whose dependent quantity is the thing to be maximized or minimized. So this is kind of the thing we want to memorize at first, right? Memorize this at first. We want an equation that relates the rates. That means we're going to get an equation that relates the quantities, and then do our implicit differentiation with respect to t. Okay. Anybody have a question? Yeah.
So what algebra did you use if the dy over dt equals negative x? I don't know why.
The same algebra as always. So,
I don't know, I just can't figure it out.
all right, sure. So 2y dy dt equals negative 2x dx dt. Good so far?
Yeah.
Divide by 2y. So negative 2x over 2y dy dt, and then 2's go away.
Oh. Alright, thank you.
Yep. No problem. So dx dt and dy dt are going to be rates that are going to be, we're thinking of those in this context as one value. So you're not going to separate out the dx dt. Other questions? Yeah.
So dx dt is a constant speed.
In this we declared it was. Yeah.
Right.
Yeah.
Will we be dealing in this class with any situations where it doesn't?
Right. Yeah. So in this particular case, I just said that's constant, but it could be that dx dt and dy dt are both changing. It could be they're both changing according to, together.
When we hit that, will that be with a third variable? Will that be with v, like v squared plus 1 or something? Will that
No, it could just be two rates that are both changing. You could something like this, where you have two rates in the same equation and they're both changing quantities. But we would be pinpointing the situation at a particular time. So it's kind of like, so what's the speed of the ladder when it's 5 feet above the ground? So what is the speed of the ladder when it's 5 feet above the ground? Well, we'd have, this would be 5, and we'd have the corresponding x, and then we'd have to know what the constant rate of the bottom of the ladder is, and then that expression computed would tell us how fast the ladder is moving down. Other questions? Yes, please.
I don't know if we're into this, but like, how do you know which one goes over the side like
Oh, because that was the question we were asking. What question were we asking? What did we want to find there? How fast is the top of the ladder falling in feet per second? What is that? That's the dy, right? How fast the top of the ladder is falling would be the change in y per time. So that was what motivated us to solve for dy dt. Now, you actually don't really even need to do this. You can just use this to plug in your values and solve for the unknown. So we could have just left it like this, plugged in a y, plugged in a dx dt, plugged in an x, and then solved for the unknown. Yeah. So these are one and the same. This one is just organized to actually give us exactly what the question was asking. But those two equations are exactly the same, just one's a rearranged version of the other. Other questions? Okay. So we have a cube, and the edges of the cube, the length of the edges, is increasing at a rate of 2 centimeters per second. We have a increasing cube, a cube that's growing, a growing cube. How fast is the volume changing when the length of each edge is 50 centimeters? So what is indicating that this is related rates? The fact that there's more than one rate of change mentioned in the problem. Do you see this? So we've got these quantities, but it's talking about more than one rate of change. What's the first rate of change that you see here? The edges of a cube increase at a rate of 2 centimeters per second. That's a rate. And then it says how fast is the volume changing? Well, that's a rate too. This is because there's more than one rate mentioned. This is indicating, and we want to find a rate of change. It's indicating that it's going to be a related rates problem. Okay, remember this is our kind of focus here. In order to get the related rates equation, it's about having a quantities equation first, and we're going to do the implicit differentiation with respect to t to get the related rates equation. So we need that quantities equation first. So before even we have the quantities equation, then we want to identify the quantities and identify the rates. So here's kind of a roadmap that you could do this. So first identify all rates, and we kind of already did that. The length of the cube is increasing at 2 centimeters per second, and then it's also talking about the volume. So the cube length per second. So cube length in centimeters per second. And volume rate in, what would that, so what would, if we were centimeters per second, what would the rate of change of volume, what would the units be in that? Centimeters cubed per second. All right, so this next step is kind of, so once you've identified the rates, well, so like what quantity is associated with this cube length rate? It's like so easy, cube length, right? And what quantity is associated with volume rate? Volume, right? So we do that. So what are the quantities for each rate? So we're talking about how fast the edge length is changing, what quantity is associated with that? Super easy question. What quantity is associated with the rate, how fast the edge length is changing? Edge length, right? Quantities are things like distance, temperature, right? So, how fast the volume is changing. What quantity is associated with that rate, how fast the volume is changing? Volume. So let's assign variables for those. So we'll call edge length S, and we'll call volume V. And so if we want the equation that relates to the rates, what do we need? We need the equation that relates to quantity. So here's our quantities, edge length and volume. We need to come up with a relationship between edge length and volume. No, we need a relationship, no, not any rates yet, right? So this doesn't have to do with any rates. The quantities equation. So what is the relationship? So it's common sense. What is the relationship between S and V? Right, yeah, so V equals S cubed. V equals S cubed. Unfortunately, confounding. Let's make the function F, okay? So V, we just want the equation right now. V equals S cubed. V equals S cubed. I made a function, but we don't need a function. We need an equation that relates those quantities. So V equals S cubed. And so now we need the related rates equation. Now we need, once we have the equation that relates to the quantities, we can derive the related rates equation. So we're going to take the derivative of both sides with respect to what? Time, right? Everything's about time. We want edge length in centimeters per second, volume in centimeters cubed per second. So we're going to take the derivative of volume with respect to time and the derivative of S cubed with respect to time. Okay, so on the left side, we're just going to get dV dt. That's all it is. It's just the derivative of volume. There's no chain rule there. It's just dV dt. But then on the right side, we need the derivative of S cubed, which is 3s squared, but times, right? S is a function of t, so times ds dt. So this is the same thing we've been doing, but now we don't have x and y anymore. We have v and s, and everything's with respect to t instead of with respect to x. Okay, and so what is it asking for? What is the equation is asking for? How fast is the volume changing? So which of those things is how fast the volume is changing? dV dt. So in order to solve for dV dt, that means we must have enough information to get everything else. All right, if we're able to solve for dV dt, then everything else in this related rates equation must be known. Okay, must be known. So that means we must know what S is. What is S? 50. And what is ds dt? That was that's how fast the edge length is changed with respect to time. So that's our 2. So we're going to plug in our 50 for S and our 2 for ds dt. So we get 3 times 50 squared times 2, and that ends up being 15,000, and then the units centimeter cubed per second. Anybody have a question? So it's about the quantities, about an equation that relates those quantities, from which we can get the related rates equation. Okay, here's a common thing students do sometimes. So we knew that S was 50, right? So couldn't we just write this equation as V equals 50 cubed? What happens now when we take the derivative? dVt equals What's the derivative of that with respect to t? 0. So if you do that, you've just stopped the cube from increasing in size. You just fixed it at 50, and you said, now how fast is the volume changing? So whenever you have a changing quantity, it has to stay as its variable until the related rates equation. Then you can plug in the 50, right? So we want to plug in the 50 into the related rates equation, not the original equation, because if we do, then it's no longer a changing quantity. We just have a cube sitting here with a side length of 50. And so its rate of change of volume is 0. It's not, the volume isn't changing. But this is a very common mistake students make. They plug in values for changing quantities before taking the derivative, and then that stops everything from changing. And you just get lots of zeros. So make sure that the changing quantities stay changing until the very last step. That's when you plug things in. Make sense? Any questions on this? Yes, please.
Why do you take the chain rule of the right and not the left?
Oh, we could. What's the derivative? We can still take the chain rule. What's the derivative of v? 1. So we could. I could have done 1 and then times dv dt. So that would have been thinking of it as chain rule.
And then why are you taking the chain rule again?
Because v and s are functions of t. So v is a function of t equals, right? And so if I'm taking the derivative with respect to t, we're thinking of this, so this is some expression of t's, the side length. Maybe it's t cubed plus the square root of t, right? So we think of it as some expression of t's, not just a variable. So then it'd be 3s, the derivative would be 3st squared times the derivative of the inside, which could be some expression of t's. So that's why we need s prime of t. Does it answer it? Yeah. Okay. Other questions? Yeah, William.
So with the DSDT,
Yeah.
so I understand that the rate for that is constant. So you DS over DT, does that symbolize like the derived value of 2?
So it would. This is the rate of change at which the side length is changing with respect to time. So in this particular problem, that's constant at 2 centimeters per second. So I don't know if that answers it. Does that answer your question?
Yeah.
So don't think of DSDT as like the result of a mastery test problem. Is that kind of what you're thinking? It's kind of like we had to do something to get that. Think of its meaning. Just think of its meaning. DSDT has a meaning, and that meaning is the rate of change of edge length with respect to time. And that value is given in the problem. So that's the way you want to think about it. The meaning of that value is rate of change of edge length with respect to time, which we know is always 2 centimeters per second in this scenario. That's the way you want to think about it, rather than thinking about that's like doing some kind of algebraic manipulation like the mastery test.
And we don't have to do that because it's a constant rate.
In this problem, yeah. In this problem, that's a constant rate of change of 2. So we can plug 2 into it. Okay, other questions? Okay, you guys try one. Here we go. So, after a spherical balloon is opened, untied, it expels helium at 150 inches cubed per minute. How fast is the radius changing when the balloon has a volume of 500 inches cubed? So let's talk about a roadmap first. What's our roadmap? Our overall goal is this, right? We know that if we want a related rates equation, that's going to come from a quantities equation. So roadmap. Identify the rates involved. Identify the quantities associated with those rates and assign variables. Okay? Then we're going to build this quantities equation. Write the equation that relates those quantities, keeping the changing quantities as variables. If it's a changing quantity, don't plug in a number. Keep it as a variable if it's a changing quantity. We want it to change. We want it to be able to change. And then we're going to derive the related rates equation. Go. Either way. Okay, get help if you're stuck. So we'll go down the rates. Did you get the rates? Just mention whether they're defined or not, whether you have values or not. Just all of them mention what are the rates. Volume, okay. That's one. To mention. Right. Any other rates mentioned? That's it. So you got rate of change of volume. So rates involved. Rate of change of volume, rate of change of radius. That's step one. Rate of change of volume, rate of change of radius. So what are the associated quantities? What are the associated quantities? So we're going to assign variables for those quantities. Volume, radius. And so now we have an equation that brings together those. Yeah, but you have change, right? So R is a function that's not an equals. Don't worry about anything. It's this, right? You just change R is a function of C. So think of this as a composite function. R is a function.
With the volume is 500.
What's dV dt? How fast the volume of the balloon is changing with respect to time? What is it? It's not 150. Negative 150. If a quantity is decreasing, its rate of change is negative, right? Remember? Radius. How do we get the radius? Where's that going to come from? It's not given. We need to get the radius. Where's that going to come from? Yeah, into this, right? So knowing that the volume is 500, we can get the radius. Whatever that is. What is it? 4.9. Nine two, one more. 4. Okay, so this is optional. You can take this equation and adjust the symbols to solve for dRdt. If you want to do that, that's fine. Or you can just use it as it is. You can just plug the values in its current form and then solve for dRdt. So either way, it's fine. So the way I'm showing it here is I'm just going to put my values in, my negative 150, and my R that came from the current volume of 500. And solve for dRdt. And let's get an answer here. Anybody have it? Nice and loud? It's not 0.49. Negative 0.49. Units? Inches per minute. Okay. Remember, 10 out of 15 is full credit. If you want to do more, it's extra credit, but work on them